Good afternoon, students. Yet I welcome all of you to yet another lecture of the course on simulation of business systems. And today we are going to cover the topic terminologies and like approaches. It's some additional terminologies and the stochastic simulation that we are talking about. What are the type of stochastic simulations that we are going to cover as part of the course? Also going to be looked into it. So this section's major learning agenda are four. The first one is we talk about the analytic, actually not the analytics, it is analytic versus the numeric methods. Okay. So, let us see how the analytic method and numeric method compares, and most of the type of variables, these are the variables to be used in simulation. Okay. And then some on the simulation like methods, and we will look into Monte Carlo simulation. So, today's topics are mostly related to slightly advanced concepts, and we will also do an example of Monte Carlo simulation, so that you can understand what is Monte Carlo simulation. So, let us get into the first topic today called as analytic versus numeric simulation or analytic versus numeric approach. And by definition, the analytic mode, okay. So, let us write it this way: analytic mode or approach, okay, uses the traditional. So, the analytical mode or approach uses the traditional mathematical and statistical techniques, Okay, they use the analytical and mathematical techniques to obtain exact information about the system that is being modeled, or what we call as that is being simulated. Okay. So, the most important thing is this approach, this mode utilizes the traditional mathematical and statistical approaches. Okay. We use traditional mathematical and statistical approaches or techniques, and why do we use that? So that we can get exact information about the system that is being modeled. So, the focus here is on exact information. Okay. We want the exact value, okay, and usually works when the system is simple. Okay. So, this is the analytic approach. The numeric approach, whereas the numeric approach, or we can call it as the method, the numeric method, okay, replaces these complex mathematical and statistical operations, with a large number of simple computations. Okay. So, what do we do is we eliminate the complex mathematical and statistical operations, or we eliminate those equations, and then we replace them with a large number. This is the important word, large number of simple computations. Okay. And focus is on obtaining an estimate of the specific characteristic of interest. Okay. So, the idea here is that our main aim is to the focus is on obtaining an estimate. Okay. Unlike, so not focused on exact information. Okay. So, we do not look for the exact info, instead we want an estimate. An estimate is, in another way to think about it, as an approximation. Okay. You want to estimate the specific characteristic of an interest. Okay. Also, usually the only method to analyze complex system or systems. Okay. So, when the system is complex, when the system is complicated, then you would rather like to use the numeric method or the estimation method, where the aim is to obtain an estimate and not an exact information, unlike the mathematical and statistical technique. And the numerical approach replaces the complex mathematical and statistical operations or the equations. Okay. These operations can also be thought as the equations. Okay. So, here you replace the equations or the mathematical operations with a large number of simple computations. You use computers to do a set of simple computations to obtain this particular thing called as an estimate, okay, or an approximation. That is the numeric method. And when the systems are complex, when you are dealing with large complex systems, then you use a numeric approach instead of the analytical mode, which is more dependent on the traditional mathematical and computational approach. So, let us here look at an simple example. Okay. And this demonstrative example, we will first try to take a look into this example in the form of an analytic approach. Okay. So, the system is, the aim is to obtain the value of x for which the f of x will be at its maximum. Okay. That is what the max concept says, the maximum part. So, you are trying to find out that value of x, particular value of x, for which the f of x, the resulting function, will be at its maximum. What will be the value of this? So, the analytical method, the analytical approach method amounts to what? Amounts is find the first derivative, or what we call as f dash x. Okay. Then equate it to 0. Okay. Then solve for x to obtain the value of x. Okay. So, let us see how it is done. So, your f of x is equal to 3x minus 0.005 x square minus 500. So, the f dash x, the first derivative, equal to d by dx of 3x, this is your y, okay, 0.005 x square minus 500. Okay. So, the which will translate to this will become 3 minus this will be 0.005 times 2 times x, and this will be 0 because the constant derivative will be 0, which will be equal to 3 minus 0.01 x. Okay. Now, the thing is, you say f dash x, the first derivative you set to equal to 0, implies d by dx, dy by dx is set to 0, implies 3 minus 0.01 x should be equated to 0, which gives you what we call as 0.01 x is equal to 3, right, which implies x is equal to 3 divided by 0.01 or equal to 300. Okay. So, the analytical method tells that at x equal to 300, f of x will be at the maximum value. And what is this? It's an exclamation, sorry. Okay. So, what is this maximum value? What is this maximum value? That maximum value is obtained by f of x is equal to 3 times x will be 300 minus 0.005 times 300 square minus 500. If you solve this equation, then you will get the value of f of x, which will be the maximum. So, this is the what we call as the exact value that we were looking for. Okay. So, the main thing is that this equation represents a simple second degree equation. Think about a simple quadratic equation, right. So, now because of this you can apply mathematical methods. You can do that and then you get the result. So, let us say instead of this, okay, if the question was if the equation was complicated, if the equation instead of this was something like this, f of x is equal to 3 times x to the power of 4 minus 0.005 times x to the power of 7 or something like this, minus 500, then it would not have been that easy like what we have done now. Okay. This would have been a complicated case. Then you might have resorted to something else. So, the same question or same problem that we are talking about, how can we actually solve this using the numerical method is what we are going to see in this slide. So, the same system, okay, the same equation 3x minus 0.005 x square minus 500, we are trying to solve this using the numerical method. So, the numerical approach, the numerical method or the numerical approach is roughly as follows. Okay. So, the rough approach is like this. First, okay, start with a value of x in a loop. Okay. Then using this x, find the value of f of x. Okay. So, you first start with the value of x in the loop, you take in a put it in a loop, a computer loop, a programming loop, and then in which you put a value of x, a particular value of x, and for that you find the value of f of x. Okay. Once you find the value of f of x, then the third one is increment the value of x to the next value, that is x1. Okay. You increment of the value of x to the next value, that is x1, right. Then 4, using the new x1, find the value of f of x1, right. So, you first use x, find the value of f of x, then increment the value of x to x1, then using that x1 find the value of f of x1. Then you compare. If f of x1, okay, is greater than f of x, okay, then x1 becomes the new best known solution, okay, and the values are updated. Then the fifth one is, continue the loop. You repeat this process until a result within an accuracy is obtained. Here you are not looking for the exact result. So, with a reasonable accuracy we can actually get this. So, let us take a look into what we call as this. Let us start with the loop where x, let us put it as x equal to 0. So, then at x equal to 0, f of x will be is equal to 3 times 0 minus 0.005 times 0 square minus 500, which will be equal to minus 500. So, at x equal to 0, f of x will be minus 500. Now, let us update x1 to be 100, okay, for the time being. So, the f of x1 is equal to 3 times 100 minus 0.005 times 100 square minus 500. Okay. So, we look into this, then that gives you what we call as, that is 300, and this is 100 square is 1000, multiply by this, this will give you 50, and this minus 500, which gives you minus 250. Okay. So, now if f of x1 is greater than f of x, implies if minus 250 is greater than minus 500. Is this correct? Yes, this is correct. Yes. Then x1 is the new best. Okay. Now, let us see what happened when we take the next x1. Okay. So, let us now increment x1 to, so now the f of x has become, so this is now x equal to 100, f of x is equal to minus 250. Now, x1 equal to 200. If that is the case, then what happens? Then f of x1 will be 3 times 200 minus 0.005 times 200 square minus 500, which is equal to 3 times 200 will be 600 minus 200 square times this will be minus 200, then minus 500, which will give you what you call as minus 100. Now, if you check this, if minus 100 is greater than minus 250. So, now you are comparing with the previous value. Okay. This 100 is being compared with what we call as the minus 250. Yes, this is true. Yes, true. The new best is x equal to 200 and f x is equal to minus 100. This is the new best. Now, let us take x1 is equal to 300. Then f of x1 will be 3 times 300 minus 0.05 times 300 square minus 500. So, that will be 900 minus 450 minus 500, which will be minus 50. So, now if you look into this value minus 50 is larger than minus 100. So, your new x will be equal to 300 and f of x will be minus 50. Okay. Now, do we stop here or do we continue? So, now we will take the next one, which we called as x1 is equal to 400. Okay. And at x1 equal to 400, we will get f of x1 will be equal to 3 times 400 minus 0.005 times 400 square minus 500, which will give you 1200 minus 800 times 500. Now, this will give you minus 100. Now, you know that at x1 equal to 400, the value has gone. So, now if minus 100 greater than minus 50, is this true? No, this is not true. So, then what happens is the new value. So, now we figure out that the best value of x, best value is somewhere between 300 and 400. Now, what you do is, now you do a loop between 300 and 400 and try to compute, do this again. So, you can see that there is a, this is what we call as the large number of computations. Okay. So, that is the reason why we end up doing a large number of computations to do this, and then now we repeat the same thing for 300 and 400 and we repeat this process. So, this approach is what we call as, this approach is called numeric approach or numeric method. Okay. You are not really trying to find out the exact value, instead you are trying to find the estimate of this. So, this will look silly for such a simple problem, but as the problem becomes complicated, as the degrees of the equations becomes larger, then you have no other choice but to basically go with this method and then find the solution to the problem. Okay. With that, now let us get into the next major concept that we are going to see as part of today, which is called as the variables. Okay. And these variables are pertaining to, okay, here we are discussing only simulation variables. Okay. We are only focused on simulation variables. We are not talking about what we call as the mathematical or programming variables. We are not talking about mathematical and programming variables. Instead, we are talking about simulation variables or variables that are used as part of your simulation model. Okay. So, most of the simulations or most types of the simulations has the following variables. Okay. So, we will list the number of variables now here, and then we will see, or the major variables here, and we see what are the main ones. The first one is the what we call as the output variables, and we will see each one of these variables in detail in the following after we list all these variables. Then the one that we call it as the lagged output variables. I will explain to you what the lagged output variables are, and they are also important in the case of simulation. Then what we have is called the external variables. Okay, we use external variables. Then after that, what we have is the policy variables. I will also explain to you what a policy variable is all about. Okay, policy variables. Then we have what we call as random variables. Okay, whereas this is similar to the probability concept. But we will see this in detail. And then the last type of variable is what we call as the deterministic variables. Okay. So, these are the major variables. The first one is the output variable, second is the lagged output variable, third is the external variable, fourth is the policy variable, fifth is the random variables, and sixth is what we call as the deterministic variable. So, we will talk about these 6 variables which are quite common. Okay. All of these 6 are common to most simulation approaches. Okay. In one way or other, these 6 variables gets used in the simulation model or simulation approach that we do. Okay. Now, then let us see what are the main thing called as the output variables. Okay. So, the output variables pertaining when in the case of for simulation, in the case of simulation, the output variables, the most important thing is they provide intermediate or final results of the analysis. Okay. So, what analysis? That is the numeric analysis, of the system. What we are focusing here is the numerical analysis of the system. So, it gives you the intermediate, okay, in between or final results of the analysis, the numeric analysis of the system. Also popularly known as, okay, we call these variables popularly known as dependent or response variables. See, somebody says I am talking about the dependent variable or response variable. What they are talking about it is they are either talking about the output variables, and the output variables provide you an intermediary or a final result as part of the numeric analysis of the system. So, the same term, the dependent variable or the response variable that people use is also the same as that of an output variable. Okay. So, major examples of output variables okay, include, okay, let us consider a specific case of a manufacturing system. We are talking about a manufacturing system. For that case, the specific variable, output variable, some of the variables included is, okay, number in the system, okay, which tells you how many parts are in the system. Okay. You are answering that question, number in the system, okay, most commonly known as number in system. So, it is an example of an output variable. Okay. Then number arrived. In a manufacturing system, it will be how many parts have arrived in the system, that will be the number arrived. Okay. How many parts arrived at the facility or the manufacturing factory. Okay. So, that is the number arrived part. Then number processed. Okay. So, how many parts are converted to finished goods for delivery to the customer. So, that is the number of parts that are processed. So, how many parts are converted to finished goods? Okay, that gives you the number processed. Then utilization. Okay, how much of the time a specific resource, let us call it as a machine, okay. Specific resource, a machine is doing productive work, okay. That is what is the utilization aspect of it. Then number in the queue, okay. It measures how many parts are waiting in a queue to get processed. So, how many parts are waiting in a queue before a machine, in front of a machine, so that it can get processed? That will be the number in the queue. Then average processing time, okay. It is how long on an average a particular machine takes to process a part, okay. So, here is an average, or what we call as an estimate, okay. They are all estimates on that regard, right. So, how long does a particular machine takes to process a particular part on an average? That is what we call as the average processing time, okay. Similarly, also maximum processing time, okay. So, this is the what is the maximum value of processing time among all individual processing times. Okay. So, what we are doing here is that you are measuring, okay, you have individual, if you are producing 100 parts, each one of the part will have an individual processing time, and from that individual processing time 100, find the maximum value, and that will be the maximum processing time. So, these kind of variables that I mentioned to you, the number in system, number arrived, number processed, all those kind of things are quietly common when you are studying any of the systems in the for simulation, and these gives you approximate idea of what is the final performance of system when the simulation is completed or when the simulation is running as time progresses. Okay. The next variable we are going to talk about is the lagged output variables. Okay. The lagged output variables are a unique category of variables in the case of simulation, because these lagged output variables can carry these variables can carry the system state information from one time period to another. Okay. Remember that we draw the graph of the behavior of the system, and on x axis we had time, and y axis there were different factors that we were measuring, and we were seeing that the behavior of the system was doing something like this and this kind of stuff. Okay. So, the time dependent behavior of the system, okay, when you carry that information of the time dependent behavior from one time instance to another, from this particular time instance to this, to this, to this. So, these time instances, the way you transfer these information to these time instances is what we call as the lagged output variables. Okay. So, they carry system state information. Remember, state means the particular status of the system at a given time. This time is a simulation time, not